Let's dive into the fascinating world of machine learning where creativity meets realism, the world of generative adversarial networks or GANs. Imagine a tool that can generate hyper-realistic images, create stunning videos, and even write compelling stories. GANs have the potential to revolutionize various industries from fashion to healthcare. So today we will discuss GAN and its types in simple terms. So let's get started with what is generative adversarial networks. So basically these GANs are a type of machine learning model that can generate new data that looks similar to a given data set. And they consist of two neural networks, a generator and a discriminator. Here the generator network takes random input, which is usually a noise, and produce outputs that resemble the data in the training set. And then the discriminator network takes this generator's output and tries to distinguish them from real data in the training set. The two networks compete with each other, with the generator trying to create outputs that the discriminator can't tell apart from the real data, and the discriminator try to correctly identify real and generated data. So in simple terms, think of it as a game between two players. Player 1 or the generator tries to create images or outputs that are so convincing that player 2 or the discriminator can't tell the difference between the generated images and real images. Then player 2 or the discriminator tries to correctly identify which images are real and which are generated. And this game continues until player 1 can create images that are so good that player 2 can't tell the difference. And the real life example of GAN in action is the ability to generate new convincing images of human faces. For example, a GAN could be trained on a dataset of celebrity faces, where the generator network would create new images of faces that look like they could be a real celebrities. And these images are generated by adding subtle variations to the images in the training set, making them look distinct yet still human alike. Then comes a type of GAN architecture. So there are different types of GAN architectures, where we will discuss just the 5 major types of GAN architectures. First comes the styleGAN. Now, the styleGAN is a specific type of GAN that was introduced in 2018, and it's an improvement on this traditional GAN, specifically designed to generate high quality images with better control over the generated image style. So in the styleGAN, the generator network is divided into two parts, a synthesis network and a style representation network. Here, the synthesis network generates the actual images, while the style representation network transforms the random noise input into a style representation that the synthesis network used to create the images. And the key innovation of styleGAN is that it introduces a style transfer capability, which allows users to modify the style of image. Example, changing the lighting, color or background while keeping the content, that is subject face, intact. And this is done by taking the synthesized image from generator and adjusting its style representation before feeding it back into the synthesis network to create a new image with the desired style. A simple real life example of styleGAN in action would be using it to change the background of a portrait. For instance, imagine a portrait of a person standing in front of a solid color background. So by applying style transfer, you could change the background to a different color pattern and even a photograph, while changing the subject and their facial features unchanged. So to summarize this, we can say styleGAN is a GAN-based model that generates high-quality images with improved control over the generated image style. And its style transfer capability enables user to modify the style of image while keeping the content intact. Then come cycleGAN. Now this cycleGAN is a type of GAN that is used to perform unsupervised image to image translation. It is designed to learn a mapping between two domains, that is different types of images, without requiring paired data or the images from both domains. A traditional GAN consists of two neural networks, that is a generator and discriminator, that compete with each other. But in cycleGAN, there are two generator networks and two discriminator networks. So here each generator map image from one domain to the another, and each discriminator network is responsible for distinguishing between real images from one domain and generated images from the corresponding generator network. And to ensure that the generators can faithfully map images between two domains, cycleGAN introduces cycle consistency constraint. Now this constraint ensures that image generated from one domain by the first generator then transferred back to its original domain by the second generator should closely resemble the original image. So a simple real life example of cycleGAN in action is transforming images between different styles or domains. So imagine a data set of photographs of cat in front of various backgrounds, example a park, living room, a forest. So here cycleGAN could learn a mapping between these images and different domains such as paintings. So with cycleGAN you could take a photograph of cat in the park and transform it into a painting of the same cat in the same park. So the same process could be applied to transform the painting back into the photograph. So to summarize this, we can say cycleGAN is a GAN-based model that can learn to map images between two domains without paired data. Its cycle consistency constraint ensures that generators can faithfully map images back and forth between two domains, which enables applications such as transforming images between different styles or domains. Then comes pix-to-pix. Now this pix-to-pix is a type of GAN used for image-to-image translation tasks similar to cycleGAN. But this pix-to-pix is designed to work with paired data, meaning that it requires input and output images from both domains. So in pix-to-pix, there are two generator network and one discriminator network. So here the first generator network map image from the input domain to the output domain, while second generator map images from output domain back to the input domain. And this discriminator distinguishes between real input-output pairs and generated input-output pairs. So this pix-to-pix architecture introduces a least squares GAN loss. Now this least square GAN loss encourages the generated images to be visually similar to the target images and consistent with the input images. This loss function is calculated for both generators, ensuring that they can map between the two domains with high fidelity. So a simple real life example of pix-to-pix in action would be transforming images from one artistic style to another. So imagine a data set of photographs of landscapes and their corresponding hand-drawn versions. So here this pix-to-pix could learn the mapping between two domains and can be used to transform a photograph of landscape into its hand-drawn counterpart. So to summarize this, we can say this pix-to-pix is a GAN-based model that performs image-to-image translation tasks using paired data. And its architecture consists of two generators and one discriminator with a loss function designed to ensure high fidelity in the generated images, which enables applications such as transforming images from one artistic style to another. Then comes starGAN. Now this starGAN is a GAN designed for multi-domain image-to-image translation tasks. So unlike this pix-to-pix, starGAN can handle multiple domains simultaneously without requiring paired data between domains. So this starGAN architecture consists of single generator and a single discriminator network, where the generator generates images from the latent vector, while discriminator distinguish between real images and generated images from the generator. So this starGAN introduces a unique domain token mechanism that enables the generator to learn a shared feature space for multiple domains. So this domain token is a learnable parameter that represents a specific domain. Now this generator will take a latent vector and a domain token as input and generate an image that is both visually pleasing and specific to that provided domain. A simple real-life example of starGAN in action would be transforming images between different styles or aesthetics. So imagine a data set containing images of animals, example dogs, cats, birds in different styles, example cartoon, sketch, watercolor. So this starGAN could learn a mapping between these styles and be used to transform an image of a dog from one style to another. For example, a photo of a dog could be transformed into its cartoon version, sketch version, or a watercolor version, all within the same model. So to summarize this, we can say starGAN is a GAN-based model designed for multi-domain image-to-image translation tasks without paired data. And its architecture consists of single generator and discriminator with a domain token mechanism that enables the generator to learn a shared feature space for multiple domains, which enables applications such as transforming images between different styles or aesthetics. Then comes progressive growing GAN. Now this progressive growing GAN is a GAN architecture that improves the stability and quality of GAN training by progressively growing the image resolution. So in traditional GANs, the generator produces an image of full resolution in a single step, which often leads to instability and low quality images. So this progressively growing GAN addresses this issue by incrementally increasing the resolution of generated images. Here, the generator gradually generates the image of higher and higher resolution, starting from low resolution images and progressively refining it. So this progressive GAN generator is divided into multiple strips that each generate a part of the image, and discriminator evaluates the generated image part by part. So as the generator increases the resolution, it trains the discriminator on the progressively higher resolution images. So here the simple real life example of progressive growing GAN in action would be generating high resolution images of objects. So imagine a data set of low resolution images of various objects, example animals, vehicles, buildings. So here this PC GAN could learn the mapping between low resolution inputs and high resolution outputs, generating high quality detailed images of objects. So to summarize this, we can say that this progressive growing GAN is a GAN architecture that improves stability and image quality by progressively growing the image resolution. Here its generator produces an image of higher and higher resolution in multiple steps, starting from the low resolution image and refining it gradually, which enables the generation of high quality images such as the objects with fine details. Thank you.